Hello and welcome back. In this video we'll start chapter 4, which is all about probability. So to begin with, we'll look at some vocabulary to make sure that we are all speaking the same language. And the first vocab term that we'll look at is what's called an event. And an event is going to be a collection of outcomes or results of a procedure. Now, this is a fairly vague term in a procedure. A procedure could be referring to an experiment that we're running. It could be something as simple as rolling a six-sided die or recording what color car drives by next. It's anything where we don't know what the outcome or result may be, and the event is just going to be describing some collection of these. So for example, if we roll a six-sided die, an example of an event might be rolling a 3. So what's important is that we can tell if we roll the die, we know if we rolled a 3 or not. It either happened or it didn't. Another one might be rolling an odd number. You'll notice here there's more than one way to roll an odd number. We might roll a 1, we might roll a 3 or a 5, but we can still tell. Once we roll the die, we know exactly if we got an odd number or not. And likewise, if we roll a number greater than 2, again, there's more than one way to roll a number greater than 2, but we will know after the result is recorded whether or not we're inside this event. Now, some events, like I was kind of mentioning, are going to be simple as opposed to non-simple, and a simple event is just one that can't be broken down into smaller events. So for instance, rolling a 3 on a die is going to be considered a simple event, whereas rolling an odd number is not simple. For the reasons that I just mentioned, rolling an odd number, there's more than one way to roll an odd number. You could roll a 1 or a 3 or a 5. Rolling a 1 or a 3 or a 5 individually, each of those would be a simple event. So rolling an odd number would not be considered a simple event. It's made up of simple events. And the sample space is the collection of all possible simple events. So when we roll a die, we can get the numbers 1, 2, 3, 4, 5, and 6. These are the simple events. You can't break, say, rolling a 6 down into smaller events. So we have those six events are just going to be all of the simple events that we can see. And typically, the sample space is going to be fairly straightforward when you're talking about a particular procedure. Identifying the simple events are just going to be the results that you read off. So some notation. We'll use a capital P to represent probability. We normally represent events with capital letters, although this is just convention. We don't have to. But when we write P and then parentheses A here, write the probability that A occurs. So the probability of A. And we will be looking at how to calculate this, how to estimate this throughout this chapter. One thing to note is that the probability that something occurs will be between 0 and 1. It could be equal to 0, it could be equal to 1, but it has to be somewhere in there. If the probability is 0, that means that the event can't occur. As in, for instance, if you roll a die and you want to see what's the probability of rolling a negative number, well, you can't roll a negative number, so the probability that happens is 0. Whereas if the probability is 1, it happens 100% of the time. So for instance, rolling a positive number, well, no matter what you roll, you'll always roll a positive number. So rolling a positive number would have a probability of 1. Means that it just always occurs. The closer to 0 the probability is, the less likely it is to happen. The closer to 1, the more likely it is to happen. So we can estimate probability, approximate probability, using procedures. We can just conduct the procedure or just observe it if we're not actually doing it ourselves. And then we just count how many times did A occur. So for instance, we could, so the way that we'll estimate the probability of A is we'll just count how many times our event happened, and we'll divide by the total number of times the procedure was repeated. What you'll notice here is that the number of times something occurred, this is the frequency. And the number of times the procedure was repeated, well, this is just the total number of things that happen. So if we divide the frequency by the total, what we have is the relative frequency. So what we're using is the relative frequency of an event as we repeat this procedure to estimate the probability that the event happens. So for instance, maybe we take a six-sided die and we roll it 100 times and then we get 12 sixes. So we might estimate the probability of rolling a 6 as 12 divided by 100. 12, because we got 12 sixes, we divide by 100 because that's how many times we rolled the die. So 12 out of 100 times we rolled a 6, so we'd estimate the probability that that happens is 0.12. Now remember that this is just an estimate, and we can calculate the exact probability as long as we're rolling a fair die, which is a pretty big assumption that we'd have to make. So we can estimate a probability when each outcome is equally likely. So this is a pretty big assumption that each of the outcomes is going to be equally likely. And the way we do this is we look at the number of different ways that A can occur, and we'll divide it by the number of simple events. Now, if you remember, the sample space is just a list of all the simple events. So another way to write this would be number of ways A occurs, and we'll divide it by the size of the sample space. Both of these are the same thing because the number of simple events, because the sample space is just a list of all the simple events. So let's do a couple of examples. Like rolling dice. So here, the probability of rolling a 6 on one die is going to be 1 out of 6. The 1 comes from there's one way to roll 6. Whereas 6, there are 6 possible die rolls. We could roll a 1, 2, 3, 4, 5, or 6. Well, that's 6 possibilities. So these are the simple events that can't be broken down anymore. So since there are 6 of them, the probability of rolling a 6 is going to be 1 out of 6. If we look at the probability of rolling an odd number, again, there are 6 possible die rolls. However, how many ways are there to roll an odd number? Well, we could roll a 1, a 3, or a 5. So if we count them, there are 3 ways to roll an odd number. So the probability of rolling an odd number would be 3 out of 6. Again, 3 ways to roll an odd number, 6 total dice rolls. So it's 3 out of 6. If we simplify this, this would be 1/2. Okay. Next up, the probability of rolling a number less than 7. So again, there are 6 total dice rolls that we could possibly have. And how many of them are less than 7? Well, we could roll a 1, a 2, a 3, a 4, a 5, or a 6. So any of the 6 dice rolls are going to be less than 7. So the probability of rolling a number less than 7 is going to be 6 out of 6, which is just 1. Meaning that we will always roll a number less than 7. This is what probability 1 means. And the probability of rolling a 7, again, there are 6 dice rolls, 6 potential dice rolls that we can have. And how many of them are 7? Well, we can't roll a 7. So there is no way to roll a 7. So the probability here, 0 divided by 6, is just 0. So this event cannot happen. With a probability of 0, this event cannot happen. So estimating probability could come down to essentially just guessing, like the example that they did in the book, where they looked at the probability of getting stuck in an elevator. And if you've ridden on elevators before, this doesn't happen very often. So the question is, well, how often, what number could we associate to doesn't happen very often? So if we think about 0.01 as a probability, as a fraction, this is 1 out of 100. So 1 out of every 100 times do we get stuck in an elevator? Probably not. So I would think that this is maybe too big of a probability. The next one is 1 out of every 1,000 times, or the bottom one, 1 out of every 10,000 times. I would think that maybe this is going to be a little bit closer to the real answer than this one. But again, this is just estimating the probability based on relevant knowledge. Ridden on some elevators before, never got stuck, so it's probably pretty unlikely. I don't hear of these stories very often. But this is entirely subjective. This is something that we're just taking a stab in the dark, trying to come up with a probability. Another way to do this, if we can't actually run the procedure, maybe it's dangerous, or we don't have enough materials to be able to run a procedure a bunch of times, we can do so in a computer, and we will model the procedure in the computer. One of the drawbacks is that we'll have to assume that we understand the procedure well enough to be able to program it into a computer, but we don't understand the procedure well enough to be able to calculate a probability. So we have to be able to plug it into a computer so that the computer can handle estimating the probability of an event occurring when running this procedure. This could be something like looking at how the sun works, for instance. We can't necessarily build very good models of the sun here on Earth. The sun is pretty big and pretty hot, so but it's just complicated enough that we might begin to understand some of the nuclear physics going on, but not well enough to be able to say this is the exact probability of, say, a solar flare happening. And the final thing that I'll mention is fractions are going to be really helpful in expressing probabilities. Normally fractions are a lot more exact. So for instance, if given the choice between writing a probability as 1/3 or 0.333 repeating forever, well, this is going to be simpler to look at. We're going to recognize this as the probability that something occurs is going to be 1 out of every 3 times. Decimals are harder to understand, and quite often we will round them either to 2 or 3 places, at which point, because we rounded, this is not exact anymore. We've left off a lot of 3's off of the end. So using fractions when dealing with probabilities is usually a good idea. It's not always the case, but as a rule of thumb, keep things as fractions.